In this video series, we will learn the fundamentals of thermodynamics. Thermodynamics is the science of motion due to heat. Before we begin to understand how heat is used to generate movement, we need to cover certain bases to understand, to establish a level of vocabulary. But we are going to build on this vocabulary still by developing our process of analysis. Our process of analysis in the engineering sciences require a system definition where we confine a domain of interest in the universe through real or imaginary boundaries. So we take the whole universe, we divide the universe into system and its surroundings, system plus surroundings make up the whole universe. The boundary between the system and the surroundings could be real or it could be imaginary. So, if you rephrase, system is the part of the universe that we are interested in, and surroundings is the rest of the universe. Then we look at how the system and surroundings interact. System and the surroundings, for our purposes, interact through heat exchange, through mass exchange, and through work exchange. We are going to define each and every one of those in relationship to the conservation laws that we will be using throughout the course. Okay, so the first window that we need to open between the system and the surroundings is a window that will allow us mass exchange. All right, this is a valve that allows mass into the system. When I put a dot on top of the letter, it indicates that that is a rate. So when I say m dot in, it is the mass flow rate that goes into my system. So of course, I can let the mass in as well as letting mass out. Again, another valve. I'm going to label this m dot rate of mass flow out of the system boundary. So my system interacts with its surroundings through mass exchange, number one. Number two, my system interacts with its surroundings by heat exchange. In other words, I might have a conducting wall or what we call a diathermal wall. And I'm going to build my vocabulary here for your reference. My first term that I wish to be remembered is the universe. We divide the universe into a system and the surroundings, and we're going to have system and surroundings interacting with one another through mass exchange, through heat exchange, and through work exchange. The heat exchange between the system and its surroundings is going to be taking place through a diathermal wall right? The diathermal wall allows us to exchange heat. So I'm going to draw a broken arrow, indicate that this is going to exchange heat, and I'm going to indicate heat as Q, and when I put a dot on top, it means that it is per unit time. So let me also put the label here, so that we can remember Q dot. Now my system and its surroundings interact also through work exchange. Now work exchange, as far as we are concerned, have three components. One of them is a surface boundary movement work. All right, so I have a piston and a cylinder. The exchange of work through the movement of the piston is due to the difference between the system pressure and the pressure of the environment. So in order for the system to be in equilibrium with its environment, in terms of the pressures, we have a piston movement. So our piston movement allow us to exchange work with the environment. There is another work exchange. This is the impeller. We can exchange work with the environment through an impeller. Rotation of the impeller is imposed on the system by the environment, and this is called the shaft work. This is the surface boundary movement work, and there is another work term that is called the flow work. Flow work is the work done on the system by the incoming streams, or work done on the environment by the outgoing streams. So we have a flow work, we have a surface boundary movement work, and we have a shaft work. We have three different kinds of work. Let's see. Flow, surface boundary movement, and shaft. Now let's take a human body as the system, and let's see whether we have any of these defined terms be related to the relationship of a human body with its surroundings. Now, just continue listening to this part by also performing this experiment onto yourself, that the human body is, let's draw our human body here, not an artistically perfect, but personally happy creature, that it has, under normal conditions, a body temperature of 36.5 degrees Celsius temperature. Now I have used a new term to define a system. Let me put it on my vocabulary. Temperature. Just to be in line, I already have used the term pressure. Let me put that on my vocabulary list as well. Now this human being, this stick person, has 36.5 degrees Celsius of temperature maintained by his or her metabolism. The environment under pleasant conditions is around 22 degrees Celsius. Now, because environment is at a lower temperature than our system, the natural consequence of this situation is that the system would like to establish thermal equilibrium with its environment. Thermal equilibrium means that we have same temperatures. I've used another term, a major term. I will capitalize it. I'll say equilibrium. Now, since our system would like to reach thermal equilibrium, temperature is a measure of the total energy of the system. Because it is a measure of the energy of the system, lower temperatures means that we have lower energies on this side, higher temperatures means that we have higher energies on that side, and the natural flow of the energy will be from higher to lower. So we will have heat flow. I will use the broken arrow. Heat flow from the system to the surroundings. This is one of the interactions of a human body with its environment by heat. That interaction is accompanied also by surface boundary movement, shaft work, and flow works as well. So let us think about the surface boundary movement work. Now we will inhale. When we inhale, our lungs and exterior expands. When we exhale, we know that our lungs and the exterior contract. This expansion and contraction process is a surface boundary movement. If you take your lungs as your system, that expansion becomes more apparent. So that is what we mean by surface boundary movement. Now the flow work or mass exchange is best explained by the inhalation and exhalation. We intake air and we exhale. We intake air, air circulates within our metabolism, some chemical transformations take place, generating energy that is maintaining this temperature, and through exhalation, we add to the environment the products of the metabolic reactions, carbon dioxide and water, in addition to the inhaled oxygen and nitrogen. So let's take our hands and let's exhale. Now, I feel, and I'm sure you feel also, that when we exhale, we feel the movement of air through our hands. If we have a lighter object in front of us, that our exhalation can move that lighter object. So if our exhalation can move that lighter object, such as a piece of paper, it means that our exhalation is doing work on that object. But if I can feel from a distance of my exhalation, it means that the air that is leaving my lungs and my mouth is pushing the molecules in front of them. Those molecules are pushing the other molecules in front of them. The other molecules are pushing the other molecules in front of them until they hit the boundary of my hand or yours. So the fact that we feel the airflow means that those molecules exert a certain amount of pressure. That my hand is not moving doesn't mean that work is not done on my hands. The work done on my hand is dissipated because there is not sufficient energy of the air molecules. Okay, so we have defined our system potato. We have defined our mass in and mass out. And we have our stick person here. We have defined some aspects of surface boundary movements. And of course, that I have been moving, that my hands were moving. And we can consider that as an example of a shaft work. All right? So we have a perfect experimental tool. I suggest that you observe your interactions, your body's interactions with its environment. When you are drinking water, you are taking in a mass. When you are breathing out, you are discarding mass. And through your metabolism, limitless number of chemical conversions are taking place in order to run this complex system of engineering. So, system, surroundings, heat, and work are going to be our staples, and every lecture, every example will have to have those components to be addressed. Defining system in relation to its environment accurately is important. And now let's define what is heat, what is work. Heat is energy in transit due to a temperature difference. Let me define it here. Heat is energy in transit due to a temperature difference. And temperature difference from this point on is going to be indicated as delta T. Delta is going to indicate difference. Delta as such is the uppercase Greek letter, and it stands for the difference. Energy in transit due to a temperature difference. Work, on the other hand, is energy in transit due to motion. Due to motion of the molecules, due to motion of impellers, due to motion of the pistons. Energy in transit. Okay. So what is energy? What is the difference between the energy and energy in transit? Let's define energy. In the simplest terms, energy can be regarded as the capacity to do work, but the fundamental definition of energy is elusive. But we are going to focus our attention to a specific type of energy, but let's define some general form of energy before we come down to this specific definition of energy. Now, from the courses of physics, we know we've learned kinetic energy. We've learned potential energy. We will pay a lot of attention in this course, in these video series, to internal energy, but there are other forms of energy, such as nuclear energy, such as electromagnetic energy, and so on and so forth. So, I will write Ke for kinetic energy, Pe for potential energy. I have this letter U for internal energy, and so forth. Now take another example. Take a ball. This ball, because of its elevation relative to a reference plane, is going to have some potential energy. If this ball is in motion in any of the directions, it's going to have a kinetic energy, and this ball itself, because we have material making up this ball, because we have molecules making up this ball, it is going to have an internal energy. Now consider that this ball is made of plastic. Within that plastic, we are going to have many carbon-hydrogen bonds. Those bonds will possess bond energies, which we are not, in this course, not interested. These bonds will vibrate. The atoms will vibrate across these bonds. We're going to have vibrational energies. If the bonds allow rotation of those molecules, we will have rotational energies, and the sum of those energies is going to constitute the internal energy of the ball. That our ball has a mass means that it's going to have its own internal energy. And of course, kinetic energy of this ball is going to depend on its mass and its velocity. The potential energy of this ball is going to depend on its mass and on its elevation relative to the gravitational field. And the internal energy of this ball is going to depend on its mass and its temperature. So, we have defined the general aspects of the energy. We have defined heat and work as energy in transit. Energy in transit, right? But these energies in transit are different from the kinetic energies, potential energies, and internal energies. We have to be very, very, very careful about that. The heat exchange occurs across a wall that allows us to exchange heat, and we call this wall a diathermal wall. We need a temperature gradient for heat exchange. For some aspects of work exchange, such as surface boundary movement or flow work, we need pressure gradients. And those energies in transit help the system reach equilibrium with its environment. And throughout this course, we are going to analyze systems that are undergoing heat exchange and mass exchange and work exchange with its environment for the purposes of designing engineering systems, such as doing power conversion, such as doing refrigeration, and so on and so forth. So, in order to be able to do that, we need certain mathematical formalism, and we're going to learn certain basic fundamental laws of nature. Some of them I have been talking about, but let's put them formally on the board, and we're going to use them in analyzing processes, in designing and developing new processes. Okay. Rule number 1. Mass is conserved. What does that mean? So let us just generate a domain boundary that our words don't mix. Mass is conserved, or mass is neither created nor destroyed. So let me take my system potato and take a picture of this system potato at time t is equal to 0, and take another picture at time t is equal to delta t, that I have allowed delta t seconds, minutes, hours, days, whatever period of time, and I let my system evolve in this time frame, and I have taken another picture. So I'm going to look at my system. Let me just call this not t0, but t is an arbitrary t, and this t is an arbitrary t plus delta t. All right? Mass at t plus delta t my picture after I allowed my system to evolve to the new state. Okay. Another term that we will be very frequently using should be equal to mass at time t that my system was at in the beginning frame that I chose, plus whatever has happened in the meantime, plus the mass entered through the system boundary, m dot in. See, this has dot, this doesn't. This means that this is mass. In other words, its units is units of mass. I will call kilograms. This is in kilograms, in the units of. But this is in kilograms per second. Remember, it was a rate. It was a flow rate. M dot in, mass, flow rate in. Now, I cannot do algebra with different systems of units. I cannot add and subtract apples and oranges. Either I have to have apples only or oranges only. As a result, I have to convert this to the same system of units. Now, if I have 1 kilogram per second flow, and if I have measured, if my delta T is 1 second, how many kilograms after so and so many seconds? Right? I have to multiply by delta T. This amount of mass entered through my system boundaries minus m dot out times delta T. That much mass has left my system boundaries in that meantime. And as far as my system potato drawn as such, I only have m dot in and m dot out. And this is my conservation of mass equation. I'm going to rearrange this equation. I will collect similar terms together. M dot at T plus delta T minus, no, there's no dot, this is mass, minus M at T is equal to m dot in minus m dot out times delta T. It's the same term. I can have them in a common parenthesis. What I will do, I will divide both sides by delta T, and I will take the limit as delta T goes to 0. M at T plus delta T minus m at T divided by delta T in the limit as delta T goes to 0 is m dot in minus m dot out. And this term altogether is time rate of change of mass within the system boundaries, and it is the difference between incoming and outgoing stream flow rates. And this is the conservation of mass. I will put it here. It is so general. dm over dt is equal to m dot in. But when I generalize, I will generalize it far broadly. I'm going to put a summation sign, and that is going to allow me to account for all the streams that is crossing the system boundary towards the system minus sigma m dot out. And that summation sign is going to account for all the streams that is crossing through my system boundary in the outward direction. This is the conservation of mass in its most general form. Now we begin with a clean environment board, and we are going to write the second fact that we are going to use throughout the semester, that the energy is conserved. So the energy is conserved is going to be, again, analyzed relative to our system and its environment. I'm going to indicate the total energy as U, internal energy, plus potential energy, plus kinetic energy. And I will apply the same strategy. I'm going to take the picture of my system at time t and at time t plus delta t, and I'm going to check what my equation is going to look like. Energy at time t plus delta t, this is U plus potential energy plus kinetic energy, is equal to energy at time t plus all the energy flows into the system. What are the modes of energy transfer into the system? We have masses bringing in their own energy, including kinetic and potential also. So we are going to have m dot in times E hat in. Now, why did I put this hat? This is total energy. This is specific energy. Energy per unit mass times delta T, right? Minus m dot out times E hat out times delta T, and we are not finished. We have to take heat, shaft work, surface boundary work, and the flow work into consideration. So I'm going to write plus Q dot times delta T plus work dot times delta T, and this work term is going to contain flow work, surface boundary movement, and the shaft work. Now let me regroup again this for in a similar fashion as I did for the mass exchange, and then let's address each and every component of this equation. Again, rearrange E at T plus delta T minus E at T to be equal to, all these terms have delta T. I'm going to collect them in a parentheses with delta T, and that in E in minus m dot out E out plus Q dot plus work dot times delta T I will divide both sides by delta T. I will take the limit as delta T goes to 0. And this term is going to represent the time rate of change of total energy within the system boundary. And it is equal to, again I will generalize, summation of all the streams that are going to enter through the system boundaries minus summation of all the streams that leave through the system boundaries plus heat plus work. Now heat is heat going through the system boundaries. Work has to be dissected into flow work, surface boundary movement, and shaft work. What is the flow work? Flow work is the wind generated by a subway in its tunnel, or the work that a fluid has to do in order to cross the system boundaries. So the fluid, which is outside the system boundaries, has to do work in order to go through the system boundaries. The fluid, if it is leaving the system boundaries, it has to do work on the environment. It has to do work on the fluids around the environment. So, let's indicate the shaft work as it is. Flow work is m dot in times p times v in, and I'm going to explain these terms. Why it is p times v, why it is p times v hat, I will explain. Of course, we have m dot out times p times v out. And then we have surface boundary movement work. And that is going to be minus p dv over dt. Now let's take this one and convince ourselves that yes, this is so. The surface boundary movement work. So, from the basic physics, we know that work is force times the displacement. Okay? The work is force times the displacement. Now, what is the force? What is the force imposed upon this piston? We have an external pressure and we have the weight of the piston doing work on the gas within the system boundary. What is pressure? Pressure is force per unit area. So work is pressure times the area times the displacement. Now, area times the displacement for a perfect cylindrical geometry is the volume. And I'm using the differential form to indicate that this is the differential movement. But when we look at the equation that we have work as additive term, now if the pressure, external pressure, is greater than the internal pressure, the displacement will be towards the system boundary, the volume will decrease, but the system energy will increase. In order to take this into consideration, we have to put a minus sign. And the reason that I use a different sign to indicate the differential work has to be noted. So, I have dE over dt, I have dV over dt. These dt terms take care of the unit consistency. In order to have this as work done, I have to have this as dt, as dt, as dt. So this is the surface boundary movement. These are the flow terms. And I am going to write on a clean board the final form of the conservation of energy as well. So when we summarize the conservation of energy on a clean board, time rate of change of total energy within the system boundaries is going to be equal to the total energy that enters through the system boundaries by mass flow total energy that leaves the system boundaries through mass flow the heat exchanged through the system boundaries, the shaft work that is done on the system or by the system. We will learn why we put everything as additive eventually, plus the flow work. I will write the flow work right underneath the energy term for you to see the similarity minus P dV over dt. Let's look at this term. Pressure is the pressure of the incoming stream. V hat is the specific volume of the incoming stream. When they are combined, P times V hat, that they have an equivalency of P times dV. But this time, the work and the flow is in the same direction, unlike the surface boundary movement. So if the work is towards the system boundary, we add. If it is away from the system boundaries, we subtract. Here, volume changes the towards. Work has to be towards, but this volume change towards the system boundary is going to be a decrease in the system volume, while the work is on the system, energy of the system has to increase, hence we put a minus in front. So this complex equation is the conservation of energy, and it is also known as the first law of thermodynamics. Now let's look at the heat term. Heat term is defined as the energy in transit due to a temperature difference. And our stick person, which was here, was transferring heat to his or her surroundings, because surroundings was at a lower temperature than the metabolic temperature of the stick person. So this heat exchange term was taking place across a diathermal wall. In other words, the wall is allowing us exchange heat. If the wall is not going to allow heat exchange, in other words, if you have an insulating layer that stops heat exchange, then we call that system adiabatic. Diathermal wall, adiabatic. When heat exchange is not taking place, we call the process an adiabatic process. We have discussed the fact that if we have a body, let's say A, which is in contact with a body B, and if they are at temperatures such that temperature of body A is greater than temperature of body B, we will have a heat flow from body A to body B until TA is equal to TB. As time goes to infinity, at time t is equal to 0. Let's summarize this example. At point of time t is equal to 0, we have a body A, which is at a temperature TA. We brought it in contact with body B, which is at a temperature of TB, which is lower than TA. And we allowed heat to flow from body A to body B. We waited for infinitely long time, and this infinitely long time depends on the circumstance. It might be a second, it might be an hour, it might be 100,000 years. We allow the system to equilibrate. The magic word, the temperatures become equal, and the situation is called the thermal equilibrium. Okay. Keep that in mind. Now let's have a piston and a cylinder arrangement. Or let's take an inflated balloon. Tied up an inflated balloon. The fact that we can inflate this balloon means that P in the balloon is going to be greater than the pressure of the surroundings. Now, if we untie this balloon, what will happen is that the contents of the balloon is going to escape until P interior is equal to the exterior pressure. So this is called the mechanical equilibrium. So we have thermal equilibrium, we have mechanical equilibrium. Let's reflect this understanding to our piston and cylinder arrangement. Now we have a gas. In this piston and cylinder arrangement, which is greater than the external pressure, if we allow this piston to equilibrate with its environment, the piston will rise until the interior pressure is equal to exterior pressure. This is mechanical equilibrium. And between this situation and this situation, we obtained work. So, we have bodies at different temperatures. We have systems that allow us to do work. Maybe we can combine them and we can convert heat to movement, heat to work. Now let's build on our vocabulary. We have defined the term adiabatic, which referred to a system where heat exchange is not permitted. We're going to also define terms that will allow us to understand, communicate certain facts about how our system and its environment is related to one another. Now when we allow mass exchange through our system boundaries, we will call the system as open. So the vocabulary continues here. We have open system. For the open systems, we are going to have mass exchange that are going to have finite amounts of mass exchange. The mass flow rates are going to be finite. For the closed systems, these terms are going to be 0. When we say open or closed, we mean open or closed for mass exchange. For heat exchange, we say that the system is adiabatic when there is no heat exchange permitted. All right, then we have to differentiate the term state from the term state of aggregation. State within the context of this course refers to the state of the system, not the state of aggregation. For the state of aggregation, such as liquid, vapor, solid, gas, or plasma, we will use the term phase. When we are talking about the state of the system, it will refer to the conditions of the system that is going to be specified by the state variables. What are those state variables? For the state variables, we have to define the terms intensive and extensive properties. Intensive properties they don't depend on the size of the system. While the extensive properties are functions of extensive properties are functions of the size of the system. Example, the price of oranges, for example, are, let's say, 5 liras per kilogram. Whether you buy half a kilogram or 10 kilograms, that price doesn't change. It's an intensive property. It doesn't depend on the size. But the money you pay, if you buy half a kilogram, you're not going to pay as much as when you buy a kilogram of oranges. So the total money you pay is an extensive property. The specific volume, specific energy are intensive properties. Let's write here. While total energy, total volume are extensive properties. And, of course, they are related to one another. Total energy is specific energy multiplied by total mass. So we defined open, closed, relative to the mass exchange. When I say an open system, we will understand that term communicates that the system allows heat exchange, mass exchange. When I say an adiabatic system, it means that the system doesn't allow for heat exchange. And state refers to the state of the system, and for a pure fluid, such as pure water, such as pure oxygen, the state of the system depends on two intensive variables. For a pure fluid, two intensive variables can define the state of a system. What are those two intensive variables that can define the state of a system? We need two variables that are not going to depend on the size of the system. We said energy, we said specific energy, we said specific volume. We also have temperature, we also have pressure. Temperature and pressure are also intensive properties. And we call them state variables. So, when we summarize, we start from state 1 of a system. We monitor the evolution of that state through a process, and this process depends on mass flow, heat flow, and work flow. And some of the times that we design this process, some other times we try to deduce what the process is. So this is what is going to be our agenda in this course. Now let's apply what we have learned so far to a simple problem of filling a tank. So let's take a bucket, an empty bucket, bring to a tap, so we designate our valves like this. We are going to fill this bucket. Our system is the bucket. The rest is our environment. We have a constant mass flow, which is m dot in. We are going to give numerical values eventually to these problems. This is a 20-liter bucket. M dot in is 1 liter per minute. How much time does it take for the bucket to fill? Quick answer. But let's do it from the formal strategy. My system is the bucket. My balance equation says that time rate of change of total mass within the system is the rate with which mass flows through the system boundary, m dot in. I only have one stream. This is an open system. No outflow. And this is constant. This is 1 liter per minute. I'm going to integrate. dm is equal to m dot in times dt from 0 to 20 times rho times rho. Rho is the fluid density. Or it is m dot divided by the specific volume. So the equation m final minus m initial is equal to m dot in times t final minus t initial is going to be a specific solution. The general solution will be m final to be equal to, or m at any time t is equal to m dot in times t. At time t is equal to 0, m initial was equal to 0. So we added the boundary conditions for the general solution. So by obtaining a general solution, now I can estimate mass in this system at any time between the time that the bucket starts to fill and the time that it is completely full, provided that my process doesn't change, remain identical. Now let me solve another example. This is my first example. Let me solve another example. The second example is going to be another tank that is being filled . That we have another container that takes in mass at m dot 1, another mass at m dot 2, and m dot 3 is the mass flow rate that leaves the system boundaries. Question is, what is m dot 3 under steady state conditions? So let's define steady state. Steady state is a process attribute that you have to have a process, that we have to have streams flowing in and out, energies flowing in and out. Here we have streams flowing in and out, and under steady state conditions, the system is invariant with respect to time. Under steady state conditions, d over dt term is equal to 0. The system does not change with respect to time. There's another condition that satisfies this mathematical this description. So let us write our material balance for this example. dm over dt. Now we are given the condition that the system is at steady state is equal to 0. This is equal to m dot 1 plus m dot 2 enters minus m dot 3. Under steady state conditions, m dot 3 must be equal to m dot 1 plus m dot 2, so that the level of the fluid within the system boundary remains the same. Total mass within the system boundary remains the same. The difference between this situation and this is that the mass within the system boundary increased continuously. However, in the second situation, the mass within the system boundary remained constant despite we had flows in and out of the system boundary. So this is going to define the condition of steady state, which is time invariance under forced flows. So steady state is time invariance under forced flows. The other time invariance condition is equilibrium. Equilibrium is time invariance under natural flows time invariance, that d over dt terms, d whatever, whether it is mass or energy or something else, is equal to 0 under natural forces, natural flows. We don't force anything. We have two blocks, TA being greater than TB. We let energy flow from A to B in the natural direction until the temperatures are equal and they do not change with time. They do not change with time. Their time derivative is 0. Equilibrium is time invariance under natural flows, while the steady state is the condition that we have time invariance, d over dt term is equal to 0, time invariance under forced flows. we force the flow to the system. We force the fluids to the system and from the system. In order for these fluids to flow through the system, we need to either put a pump or a compressor, but we have to direct the flow to the system boundary. Forced flows. Natural flows eventually will come to a cease. Now, say that we turn off this valve. Will it stop m.1 and m.2? Not necessarily. That m.1 and m.2 will continue to flow and the system will overflow eventually. So this is forced flow. If it were under natural flows, that our systems would equilibrate and the flow would stop. The natural flow equivalent of this filling problem would be that we have a chamber which is filled up to this height, connected to another chamber which is empty, that when we open this valve, natural direction of flow will be from this chamber to this one until they have the same level of liquid, or if it's the gas, the same pressure in both chambers. So this would have been a natural flow, and this would have indicated an equilibrium condition, but not a steady state condition. So this is something that you have to just observe and exercise a lot to understand and to differentiate those two concepts that are represented by the same mathematical identity, that d over dt is equal to 0, but they reflect two totally different physical situations.